Hello everyone. In this video, we will examine topic 4.4 wave behavior, and we will focus in on two-dimensional and three-dimensional interference patterns and path difference. So, to return to two-dimensional and three-dimensional interference, there are cases, many of them, where it's important to understand how interference works when there is not a double slit. So the double slit experiment is an important and seminal and foundational experiment, but it is not the only game in town. So consider any two sources producing coherent waves, and notice this can be of any type. Remember that coherent means that they produce peaks at the same time and troughs at the same time. They're in phase. But this could be water waves, these could be three-dimensional sound waves, and we might still be able to ask, where do we find constructive interference or destructive interference? And in particular, we're going to examine the case of two sources with a fixed wavelength distance between them. So examine this diagram here, all right? Consider the red points. Notice that all the red points lie on a line where the wavefronts cross. So just like the double slit experiment, we may consider that line, okay, right there, as being a point where we'll find constructive interference. If these two sources are sound waves, we would expect to find loud sounds right here. Notice these are coherent sounds, so in reality, this would be very annoying to listen to. It would be a single frequency only. Notice these black spots here. What is going on with them? Well, notice that the blue wavefront coming from S2 along that black dot at R is exactly halfway between the green wavefronts, the wavefronts coming from S1. And that means that along that line right there, we might expect destructive interference. And we can make this more formal. This right here is a diagram connecting sort of lines where we would find constructive interference in red and connecting lines where we might find destructive interference in black. Notice that delta R is the path difference. So delta R is 0 along a line equidistant from both sources. Notice that at any point along that red line, you're at the same distance from the green source and the blue source. And then this delta R, at any point along this line, you'll find that the path difference is exactly one wavelength. It's longer to blue than it is to green by exactly one wavelength. And because the two sources are, count them, 1, 2 wavelengths apart, then we only have one line here of constructive interference at 2 wavelengths apart. You would see more or additional red lines as these sources get further and further apart. So, to measure this, you could measure this kind of phenomenon using many different things. A setup you should be familiar with is one in which you have two speakers producing waves. This little setup right here is designed to measure the pattern of loud and soft sounds. Notice it's as if you're sort of cutting the diagram with a straight line right here, so you would feel here soft, loud, soft, loud, soft, loud, soft, and so on and so forth, as you moved along the wall in front of the two speakers, as the speakers produce outgoing waves, like that. And of course, these are wavefront diagrams, so they show the two waves sort of superimposed upon one another. But a better sort of representation of the combination of them might be found in this simulation here. And we can see that those lines of constructive and destructive interference are visible. The destructive lines, I think, are a little easier to see. You can see sort of the pattern of bright blue and dark sort of fade out along a sort of radiated pattern from the sources. And you can see sort of two of those in the top half on the right, and then two of those in the bottom half on the right. And then the points of constructive interference you would find in the center, where you see those bright blue and black bands. If I decrease the brightness here, okay, you can see that those are the ones that come back most brightly, and those are the bands of constructive interference. If I move to the three-dimensional view, the destructive bands or lines pop out even more extremely, and those high amplitude oscillations of constructive interference are also fairly easily visible. Okay, and this is an example of two sources, but of course you could have many sources depending on the circumstance. So this is an example where you would have four sources, and if we give it a little bit of time, you'll see that as the waves interact, they can make beautiful patterns, but there are notable points where you might see sort of brighter or dimmer structures. So this is a complex interference pattern. We won't be dealing with anything as complex as this, but it's important to recognize that these kind of things happen. We only see this kind of circumstance with sound in a few particular places. Sometimes the acoustics of a particular room mean that instrumentalists who are playing the same note need to be careful about where they're located or where the audience is located. But it's not common to encounter this particular phenomenon.